And then there's lots of other over-the-top codecs. You go to watch something on the web, you don't know what codec you're running perhaps, and maybe you don't care. And that's going to be part of our future. And then we have lots of ways to transport as well. Now I want to talk about one little additional standard, which is not a SMPTE standard, it's an AES standard. But the reason I mention it is because I was raving on about how Ethernet and IP are becoming very powerful ways to hook things up. And standards are in development for that. But one thing that's missing is audio. And as us television people know, that's the noise that goes along with the picture. But it is really important to a lot of people, even to us nowadays. And in their wisdom, the AES figured out that they need to do something with networks as well. They discovered that a lot of people were doing audio over IP in a proprietary way. So they very quickly developed the AES 67 standard, which was published in the fall.
Yeah, just right around IBC.
Right around IBC.
Yeah, just after.
And basically it's AES digital audio over IP packets. Very cool. It's an AES standard. It was called AES X192. It was that working group, TGS CO212H, if anybody cares. The bigger problem they discovered were all these people were building stuff, and it didn't plug and play. You plug one into the other and lights don't go on, nothing works. And Reveno was one who came to the table with AES and said, we really want this, we really want to work with you. And I think they arm twisted these other guys that are all nodding and say, yeah, there is ultimately a benefit for us. It's not early days anymore, everybody wants to do this, we need to plug and play. So the goal, like every standard, is interoperability. So it deals with things such as synchronization and the clocks used for the media, because when you're going over packets, you have to transport a clock by some other means than just a carrier on the wire. Encoding and streaming of the content, stream descriptions, connection management, and then ways to provide low latency. Sufficiently low latency can be used for stage monitoring. So you have to get within 10 milliseconds of your output to be able to monitor correctly for a musician, for example. So this is what they're doing with AES 67. This is the last missing piece, in my mind, of what we need for media over IP networks. We have SDI in 2022 with embedded audio. We have Genlock in 2059. We have AES 67 to transport AES audio. So the only thing really missing over IP now is how we control things. So there's another group. It's an ad hoc group. Is it still an ad hoc group, Alan, or is it a drafting group? Now a drafting group. Just changed the name, they do the same thing. And they're developing standards for media device control over IP networks. Now you say, oh, come on, we control stuff over IP all the time, and sure you do. But you can't buy a brand X control panel with a brand Z product unless it's very specifically stated and expect them to play nicely. So the goal here was to develop a single command and control infrastructure tool set. Something that would let all manufacturers build products that could work with each other and put the features and the competitive stuff up on the top of the product where it belongs, and under the hood, they still all play together nicely. And they want this to be IP-centric, needs to run on IP networks. Reasons, well, coexistence with the rest of the world. Let's face it, everything runs on IP networks. And we can leverage existing services. We don't have to invent as much, because IP networks are full of services. We've done this in the past. How many people remember ES Bus? How many people have ever implemented something with ES Bus? Right. Now you know why my hair is white. That did not work. ES Bus was a wonderfully thought through, brilliant science project. Thank you. Actually, you guys did something. You did something. You wouldn't dare put your hand up. I met 5 people, one of whom was the actual originator, Merrick Grenham, and it was a wonderful piece of work. We then went on to map it onto a network we called VSLAN, and that was back in the early 90s. Equally successful. Thankfully, I never had to touch ESLAN. Meanwhile, the successful stuff to control equipment has been things like Sony 19 VTR protocol, which to this day will still run your servers, or VDCP, which is the disk-based extension to that, or NDCP, which is VDCP over a network. But these remain proprietary implementations, and you plug brand X into brand Y, and most things work, but oh, when you push rewind, it resets the time code reader. Okay, get close. So, the rationale here is a single control method. It allows manufacturers and system builders a uniform API to everything they need. It's all a common API. It contains automated device discovery and capability discovery. So you plug a product in the network, the devices in the network, and find out what it is and what it can do, and what it cannot do by inference. We want to be able to span everything from a single point-to-point connection to the global internet. I should be able to plug in a control panel here and steer a camera in Australia. It needs to be internet friendly so that that can happen. It has to respond in real time for those applications. And no more single point-to-point wires containing some funny connector wired in some funny way to control some particular device. Again, the goal, interoperability. So they're creating a set of documents. The core framework describes the core framework for the system. And it will then go along with documents describing base capabilities for devices, protocols to be used on the wire. I'm going to use wire loosely, but protocols to be used in communication. And then also how discovery works. So a mechanism like discovery can tell a device what another device can do. The architectures the network will support. And then how to actually build a device, a capability interface, how you actually build up the model of your device so that another device can connect to it and discover it correctly. And like UHDTV, there's a glossary of terms we need. We're inventing them as we go, trying not to use redundant terms that are used elsewhere and so on, and it's not easy. So these are the current documents that are being produced by this group. These are standards documents. And their current status, I don't have a status slide. Alan, do you recall?
The core documents are finished.
Core documents are finished.
The capability document is almost done.
Right.
And in the process, they discovered that some
Right.
changes had to be made to the core, so they're revising the core.
Right. And it's all going back to full committee draft ballot, I guess.
Yeah, they're almost ready for that.
Okay. So we're within a year of the standard being
Actually, the
published.
revisions are, I think, are almost ready for DP.
Okay. Good. So very soon now. Whether this will be successful remains to be seen. If we did it right, then it will. If, like ES Bus and ES Land, we've really missed the point, well, we'll go in the same bin as them eventually. But I think this time, especially because services like Discovery, basic capabilities and wire protocols are using all existing off-the-shelf stuff. So for example, we're using UPnP, Universal Plug and Play. At home, you buy a printer, you turn on the printer, you go to your computer, it's found the printer is all configured. That's inside this. We don't need to invent that nonsense. We just need to apply it. So that, I think, is why the MDCP, Media Device Control Protocol standard, will actually gain some success and some traction. We have another drafting group for lip sync, and I'll tell you quickly about this. I think you've heard about this before. This is a single solution for AV synchronization, the oldest and the most annoying problem in my mind in the industry. Looking for a solution that is robust and will withstand alteration of the content. So when somebody up or down converts the video and it adds a lower third and it crops the sides to put panels on it, we still want to be able to somehow measure that video for lip sync purposes. Same with audio. When somebody ducks the audio or whatever, it still has to work. It needs to work across many transports and many storage methods. We transport and store things in many ways. It has to be simple and inexpensive to implement. If it's $10,000 a node, you're not going to buy it. If you can get it added to the DNC connector on a product for a premium, you'd probably consider using it. You need something that works in service. So when you're on the air 24/7, you can monitor lip sync and correct it if necessary. And something that can be extended beyond the end of our realm. Our realm ends at the point of demarcation, be it a transmitter or out to a network usually. Well, for you network distributor people, maybe not. But the SMPTE stuff tends to stop at the edge of the broadcast world. And the distribution world, transmission world, consumer environment aren't SMPTE worlds. But we want to come up with a standard that could be applied there equally. And the I word, we want something interoperable. Lip sync breaks everywhere. There's a horrible little eye chart. Even in production systems, we can see lip sync breaking in many, many places. And you may want to fix it, or you may simply want to identify that it's broken because you know it will be fixed downstream. But measurement of it is key, and in order to fix it, you have to measure. So the way we do it is using a technique called fingerprinting. We basically measure unique criteria about the audio and video, and we call this the fingerprint. The analysis is done on a frame-by-frame basis of the video. And what we're looking at is frame-by-frame change based on luminance and based on zones of the picture. We do that to minimize complexity. We don't need the chroma, we got the luma. And we don't need the whole picture, we just need the important central action area of the picture. Changes there are usually the most manifest changes, and they're the ones the viewer's looking at anyway. We've got talking heads front and center. We also do audio analysis using a sample by sample, simple method of envelope versus mean. We just look from a sample to sample basis, see if the audio is going up, going down. We decimate that down on a video frame basis to give a fingerprint associated with the audio. The standard also then covers packaging of it into a container, so you can ship it around somehow. And then we describe how to ship it over SDI, also in fact over IP and over MPEG transport streams, and how we attach it to files. The way it works is really simple.